No? You can hear me? A little bit. I don't know if this is working. Maybe we need to, let's see. Is this better? I think it's a bit better. I don't want the echo though. How about now? Good, okay. Can people in the on Zoom hear me? If there are people?
Yes,
or
we
YouTube.
can hear you.
Okay, somebody said they can hear us. That's good. Always good to know. Okay, looks like this is live as well. Yeah, we'll start in a minute. Just to make sure other people also join. I see there are some people in the other room. That's good. There are some people online. That's also good. Cool. I'll get rid of this first. It kicked me out. I don't know why. Okay. Let's go to laser pointer, I guess. Are we still waiting for the bell? Does that still work? No, the bell doesn't work here? Really? Okay. It's been a while since I taught here. It was last year, so let's see. Okay, we should get started if it doesn't work. Okay, yeah, let's get started. I assume everything is working. If not, let me know, Mohammed and everyone. Welcome to a new semester of digital design and computer architecture. It's good to see a full room. And I think there are some people in the other room, but my eyes don't work very well for that small picture in the back. So welcome everyone online as well. We're going to have a full semester of digital design and computer architecture. I hope you'll enjoy it. If you don't, I hope at least you can tolerate it. Okay, so let's get started. I think this first lecture is going to be very easy. I'm going to be very high level. Just the goal is to motivate you why we're studying these things and what's happening in computer architecture in general. Computer architecture is really the design of systems like this, like this, like this, and things that we don't see today here, like data centers. How do they work? Basically anything that has some computation and memory capability in it. And we're going to talk about those. But in this first lecture, it's going to be mainly motivational. But before we start, okay, I don't know why that doesn't work. So do I have to use this one? Okay, I'll use this one. So I'll give you an introduction of myself. I've been a professor here for some time. Before that, I was at Carnegie Mellon University as a professor. And then I moved part of my group here. Before that, I was at Microsoft Research as a researcher. I started the computer architecture group there. So we did a lot of exciting things. And then over my career, I worked at different places. As you can see, some names over here. So, okay, wrong one. This is not working very well. Yeah, these are some places I worked at. And I got my PhD from University of Texas at Austin in 2006. And before that, I was a student like you, as a bachelor student like you, I should say, because you're always a student, right? Being a student never ends, in my opinion, in life. That's the goal of life. You always learn something. But a bachelor student, you don't be many, many times, let's say. So I was a bachelor student at University of Michigan between 1997 and 2000. And I got degrees in computer engineering and psychology. And this was one of the courses, at least a version of this was one of the courses I took in my second semester in the computer engineering degree, and I loved it. Clearly, I work in this area a lot, and hopefully you'll like it as much as I do. But I also understand that not all of you will like it as much as I do. So hopefully, even if you don't like it, even if you don't like the material, hopefully you'll learn something from it, and it will enhance you in some way. So keep an open mind. Things you don't like still may enhance you, right? In fact, sometimes things we don't like enhance us even more than things we like. So it's good to think about that. Okay, I do research and teaching in this topic, computer architecture. systems, hardware security, bioinformatics. I'm going to talk about a lot of these actually today, just to give you an overview of things. We specifically focus on a lot of things over here that I'm not going to bore you with at this point, but that's how it is. Okay, we may talk about it. This is me before COVID. Actually, this is almost right before COVID. You may guess where this is. Does anybody know where this is? It's in Zurich. No, I'm bold enough. Okay, yeah. Where? Not exactly botanical gardens, but that's a good guess. Anybody else? I like looking at pictures and guessing things, art and architecture. This, I think, at Reiter Park. Okay, anyway, I think a better picture of me might be this one. Well, somehow this doesn't work. This was a piece of art made by one of the students who took this course last semester in spring 2022. And she's extremely creative. If you're interested in her artwork, you can look at her artwork. In fact, you can buy her artwork if you want. But I like creative things. Let me put it that way. There's another picture that made by her. Apparently, I had long hair back then, so not anymore. Okay, moving away from a little bit more fun to more fun. I think I don't like this one that much because computers is. So how do I get rid of this? Yeah. Let's go back to automatic over here. And do we really need this video panel? I guess not. Okay. Yeah, this is our current mission in my group. As I said, we do research on many topics, but the fundamental goal is to build fundamentally better computers. So what does it mean to build fundamentally better computers? These are some directions. We're not going to talk a whole lot about everything over here, but I want to give you some examples of this today so that you keep the bigger picture in mind. Basically, today we're designing very, very complicated systems. And over the course of 25 lectures or so, you will see how complicated they are. There are a lot of principles, there are a lot of ideas that go into the design of computing systems today. But unfortunately, we're still falling short. That's why it's important to keep doing research and keep generating new ideas on how to design better computing systems. The question is, what does it mean to be better, right? And there are many, many aspects of better. And these are some metrics that we're trying to make better. For example, security, reliability, safety of computer architectures. Can we depend on computers? Can we trust them with our lives? Can they make decisions for us that we can actually trust, as opposed to giving us garbage, like what may be happening sometimes today, right? If you use ChatGPT, you will see that it gives you garbage sometimes. You cannot trust it, right? How do you trust something like that? That's at the software level. There is also at the hardware level things that you may not trust. So how can we build systems that are trustworthy? Today's systems are very energy hungry, and also as a result, low performance. How can we design fundamentally energy efficient systems so that we can make systems much more sustainable going into the future? Can we design artificial intelligence without really destroying the climate of the world? These are good questions to ask because today's artificial intelligence systems are extremely inefficient and they're really destroying the sustainability goals that we want to have. And they're going to become much, much worse if we keep going on the same trajectory. So we're going to talk about data-centric architectures today a little bit, memory-centric, so keep that in mind. How do we design low latency and predictable architectures? How can we make our systems, again, much faster as well as predictable? These two things are actually different, and I like pointing this out because low latency sounds good. You want to get the answer quickly. You want to do something very quickly, right? That's what's low latency. Ideally, you would like to get the answer quicker. But this is very different from predictable systems. Predictable latency. I like giving the example from trams, for example. You don't want your trams to be as low latency as possible. You want your trams to be predictable because when I want to catch my tram, I want to know that it's predictably going to leave at, I don't know, 3 p.m. If it's lower latency, if it leaves at 2:58 p.m., and if I arrive at 2:59 p.m., well, too bad. It's low latency. Well, useless to me. In fact, it was worse for me because I had to wait for the next tram now. From my perspective, the latency increased. So predictable timing is very different from low latency, and these are actually important for different things. Hopefully that makes sense. As opposed to if I have a DNA test, for example, that's really important for my life, I want low latency over there. I want to get the answer quickly because I want to act on that quickly so that I can actually get the treatment that I need, right? So these are different things, as you can see, and applied in different ways. But these are both important. And then there's a lot of interesting things that's going on today in machine learning, genomics, medicine, health, many different types of domains where we need to analyze data and understand what's going on so that we can make decisions. So building systems that are efficient for those is really important. That's something that we work on also. Okay, this is my research group. You'll get to meet a lot of these. This is actually pre-COVID also. So some of these people are gone, but you'll meet different people in the research group. If you want to learn more about the research group, you can read our newsletters. We're quite late in the 2022 newsletter. We're going to release that also. But you can learn more about us. I'm proud of my students. These are PhD and postdoc alumni. Some of the people are actually here. There's also bachelor's and master's alumni, and we actually do a lot of research with undergraduate students as well. I will mention that. Actually, some of these students over here, I cannot point, but some of these students over here were bachelor students like you, and they went on to receive dissertation awards, as you can see. Okay, let me just to give you an overview of the sequence of courses in computer architecture here. You're basically sitting in the first one right now. That's the first computer architecture and digital design course. But we also have a seminar in computer architecture. If you enjoy these topics, I'd recommend you take the seminar. It's a much smaller course, like 20 students. And you get to present in that, and you get to read cutting edge research. You get to develop your presentation skills, basically. And then there's a more advanced computer architecture course where we go into more advanced topics building on this. We may actually revisit these slides later on. And you can find all of those courses, including the link to this course on our website. So there are also other courses that I will briefly mention. I should mention that this is not the first time we're teaching this course. There are previous editions. So you can actually look at the previous editions and guess what might happen in the next lecture. I might surprise you, but usually it's quite predictable, basically. This is called last time prediction. So existing processors, existing systems actually do a lot of prediction, which is very similar to how humans do things, right? We predict things based on our mental model and understanding and past experience. So based on what has happened in the past, you can predict that what's going to happen this semester is going to be reasonably similar. There could be some differences here and there, right? So if you're interested in learning what might come up next, you can look at last year's and the previous year's editions. The longer you go back, the likelihood of divergence from this semester may increase. Okay, that's true for computers also, actually, by the way. Not necessarily, but some in prediction mechanisms that we employ. We actually are going to see a lot of prediction mechanisms in this course when we get to especially lectures 15, 16, 17, 18, when we talk about branch prediction, for example. Okay, and then these are other courses that I'm not going to bore you with, but these are for your reference links. So if you want to, for example, consider taking a seminar course after this, you can go and look at what might have happened in past seminar courses and what the course looks like. Okay, I mean, we also release a lot of videos, so if you're interested, you can take a look at these things. Okay, let me now jump into basic goals and structure of DDCA. I'll abbreviate it as DDCA because digital design and computer architecture tends to be too long. The older name of this course, digital circuits, is not accurate. It's not about digital circuits. It's really about computer architecture and digital design. And there's the German name, Digitaltechnik, I think. I don't think that's also accurate for the contents of the course. Okay, so basically, this is what we will learn in this course. That's my goal. My goal is to give you the basics of how computers work today. And not just how any computer works, it's a broad set of computers. Like, what are the principles that are employed in a broad set of systems that we design today? And this is I'm proud that this is actually a quite cutting edge course. We study a lot of cutting edge computers. We don't just look at a pipelined computer that was the state of the art in 1980s. We look at what's today out there is state of the art in 2022. And what might actually come up, well, 2023 right now, what might actually come up in 2025 also. Of course, to be able to get there, you need to start with the basics. So that's what we will do. We will start with the basics. That's what from the ground up means. We will start up with the transistor, for example. You don't need a physics knowledge for this course, although I assume many people have taken physics in high school. Can I see a show of hands? How many people have taken physics? That's good. How many people have not taken physics? I guess we should ask that. Okay, that's interesting. Yeah, that's fine. How many people who have taken physics did not enjoy physics? Don't be shy. I'm not going to grade you based on this answer. Okay. How many people have taken physics did enjoy physics? Okay, that's good. That's good. If you enjoyed physics, this is basically going to build on physics, but it will not require physics, because everything that we're going to do is built on physical principles, right? So if you're taking, how many people have taken programming? Hopefully everyone here. How many people have not taken programming? So there's, are you sure? You've never programmed in your life? Oh, that is cool. Okay, fine. Yeah, but you know programming somehow. So, okay, fine. You will need it a little bit here. But again, we're not going to, it's not necessarily required. So let me see the hands again. How many people have not taken programming? Okay, so there are some people, interesting, at school formally. Yeah. It's fine. I mean, I guess when I was at high school, I did take programming, but it was nothing like I understood what was going on, right? So here we were going to go understand what's going on, basically. You might have programmed in Python, Java. Who programmed in Python? Okay. Who programmed in Java? Okay. Who programmed in C? Okay, that's not bad. Who programmed in Perl? Okay. Nobody likes Perl. That's fine. But basically, you program in some language and you try to write an algorithm and solve things using your program. But what happens underneath in the device? How many people know about that? Okay, maybe so far. How many people do not know about that? Like how those programs get executed. Okay, that's good. So that's what we will learn here from the basics. We're going to take a bottom-up approach, meaning we're not going to start with the program and go down. We're going to start with the transistor at the very basic level, abstract it as a switch, and then build up circuits on top of it. And then we're going to connect it to the instructions that are executed on the computer. And then there's a path, a part where the programming language actually gets translated into those instructions. So you will see that a little bit also. So it's actually a pretty intense course. We'll actually cover a lot of things. I should say that. I should warn you right now. But if you actually, in my opinion, if you actually pay attention to the lectures, study, and have a learning mindset, I believe you will learn a lot. And that's what I did when I took this course in 1998. And I really enjoyed understanding how computers work. And then you can actually, the next step is, can you do much better? Okay, so basically, we will kind of study how something like this works. This is actually not state of the art anymore. I believe this is an Apple M1 Ultra system. They have M2 now. I don't know, maybe they have something else that I didn't look at. But you can see that this is a chip over here. It's actually a system on a chip because it has multiple processors, many accelerators over here, and a lot of on-chip memory caches. And then we're going to see how things happen inside here, again, from the ground up. And then we're going to see how memory, which is a bigger component, as you can see in this picture, is designed. And we're going to also talk about storage, which is actually, I would say, special case of memory. It's still a memory device, but it happens to be non-volatile. It happens to not lose data when you power it off. So you can see that the system is computation, main memory, storage, and then there are sensors. We're not going to talk a lot about sensors over here, unfortunately, because we just don't have time. But keep this in mind, basically. We're going to talk a lot about, in the end, you should be able to understand the principles that go into different components that are integrated in a system like this. So that sounds cool, right? Somebody's saying that sounds cool outside also. Okay, so let me give you the major high-level goals of this course. Basically, clearly our focus is digital design and computer architecture. We'd like to understand the basics. So we start with the basics, understand the principles of design, and my focus is on principles and their trade-offs. Because you will see that there are many, many ways that something can be designed. An instruction can be processed, for example. It's all about the trade-offs of the different ideas that you come up with. You can actually come up with new ideas also, even right now on these topics. The question is, what are the trade-offs and what are the fundamental trade-offs between these different design principles and ideas? And we would like to understand the precedents. What precedent is what people have done in the past, right? That's a very good way of understanding the basics and principles. So that's the main focus of this course, basically. Of course, I will inject cutting-edge research over here because I believe cutting-edge research and what's going on right now is extremely important to inject in a fundamental course because that's what you are the future, basically. You are going to build the future systems. If you don't know exactly what, if you don't know like the field right now, at least some general idea of what may be going on in the field, I find it not so motivating that you will be able to do that. It's better if you start rebuilding the world in the future from today, as opposed to 10 years from now. So I don't like the idea of saying, okay, these are the basics, and you don't need to know about what's going on right now. Stay in 1980s, 1990s, I don't know, 2000s. You should really think about 2030s today. But of course, understanding the basics. So basically, based on such understanding, we'll learn how a modern computer works underneath. We'll evaluate trade-offs of different designs and ideas. And you will implement this principal design, a very, very simple microprocessor in the labs. The labs are, unfortunately, they have to be simple. Well, I think a lot of people like the labs. I call them simple, but some of you may not find it simple clearly because you're going to go through it. But you will see it's a relatively simple design. You will not implement designs we will talk about in the lectures because it's not realistically feasible in a semester to do that, basically. I would love for you to implement a machine learning accelerator in your labs, but this is your first course in digital design. You're not going to do that, basically. Okay, it's going to be a simple microprocessor. Hopefully, the goal is in the future, you can actually do other things. And during the labs, you will learn to systematically debug increasingly complex systems because that's what the labs are like. And hopefully, all of these will enable you to develop new out-of-the-box designs and solve new problems out in the field. I think I've already said this. Okay, so why? I think this is my answer. This answer can be interpreted in a superficial way or a deeper way, I guess, like everything else in the world. Superficial way is, you have to tolerate it because you need to get a computer science degree for some other thing, right? Yes. But the deeper way is, I believe if you want to call yourself a computer scientist, you should really know how things work underneath. Because you're a computer scientist, right? If you don't know, who will know? Think about it that way. Right? If your abstraction layer is Python, and Python, somebody asks you, how does Python get executed? How does this really work? And you say some, I don't know, magic. Then why are you a computer scientist? Maybe you should just be a Python engineer, right? You see what I mean? Okay, so keep this in mind, basically. Understanding how things work underneath enables you to really be what you claim to be, in my opinion. Okay, what you will claim to be, of course, you're not computer scientists yet. Okay, but I think beyond that, regardless of your future direction, I think what we cover in this course could be useful, even in areas that are not applicable to computer science, in my opinion, because, well, some of these are applicable, but some of these are so fundamental. These trade-offs are so fundamental that they appear in many, many aspects of life. In fact, I'll give you examples from architecture today, later on. But what we will cover enables you to design better hardware, of course, but it will also enable you to think about how to design better software, design better systems, entire systems, hardware, software. In fact, that's what's happening today. Everybody who's doing cutting-edge work, and I say work, not research, developing cutting-edge systems to execute machine learning applications, for example, they're not designing hardware. They're not designing software, I should say hardware only. They're not designing software only. They're designing an entire system. They're designing the hardware, the software, and everything, programming model. So they're really building the full system. And if you really want to be at the cutting edge, you should really understand what's going on. Of course, make better trade-offs in design. You'll understand why computers behave the way they do. I'm not going to promise you will understand everything because even we don't still understand everything here. And that's one of our goals in research. But I think more generally, it will enable you to solve problems better. And this is applicable beyond computer science, in my opinion. And other things that are interesting and applicable, I believe, are think in parallel. So hardware is very inherently parallel. So parallelism is really inherent in the designs that you will do in your labs, for example. And you will need to orchestrate that parallelism. And I think that's a very, very useful skill to have in life in general. How do you orchestrate parallelism? Right? I mean, certainly in computer science also. And maybe most importantly, thinking critically. So I think reasons why we will cover a lot of ideas and trade-offs. I'd like you to think critically as much as possible about the idea so that you can evaluate the trade-offs, so that you can make better decisions or the right decisions given some constraints and some goals, of course. And again, this is applicable beyond this course. So I would suggest thinking critically as much as possible. Whenever I give you an idea, for example, think about the upsides and the downsides. What could this enable better, or what could this make worse? And every idea is like that. I think this is true for every idea in the world, not just what we will cover, but everything has upsides and downsides. It's good to know what are those upsides and downsides. And it's good to figure out when you can use the idea such that the upsides are maximized and the downsides are minimized, or combine ideas, or come up with new ideas, building on the past, such that you get better upsides and better downsides, let's say. Okay, there could be more, and we will discuss more. Any questions so far? Okay, I may not see your hand. If I don't see your hand, you should shout, I think. Okay, so these are course components. I wanted to go through this a little bit, but clearly we have lectures. That's for understanding the concepts. We have readings for reinforcing and going deeper. We have homeworks to prepare you for solving the problems. And then we have labs, hands-on experience in some concepts that we cover in lectures. And then we have the exam, which many of you may be scared about right now. It's a test of understanding. I don't necessarily want the exam, but it has to be there. I'm on your side on this one. I don't necessarily believe in exams, but that's how it is. That's how the, let's say, existing system is set up. As I said, you can rebuild the future in a different way. That's your responsibility, I believe, going into the future. And then we have extra credit assignments that are fundamental and simple. These are easy points, I believe. So lectures essentially provide you the fundamentals. Lectures connect with readings, homeworks, labs, and exam. So lectures enable you to actually understand the concept so that you can do better in all of these. Now, if you ask me if any of these are required, I would say probably none of these are required to pass the course. Well, you need to do the labs and exam probably. But in terms of lectures, readings, and homeworks, I don't think any of these are required as long as you understand the material and you can solve things. But if you attend the lectures, if you actually do the readings and solve the homeworks, you will have a better shot at doing better at the exam, I will say. Okay, so basically you have a lot of freedom in this course. I don't take any attendance. I don't believe in it, as I said. So you will need to think about how you approach the course. That's why I wanted to mention it early on. So my advice is not to fret too much about the exam, because that's counterproductive. But take the course as a learning experience right now, and I don't know, enjoy the lectures, enjoy the scholarship, and try to understand more and think about the trade-offs. Try to improve yourself, basically. Exam you will need to deal with, no question about that. That's a reality, right? I'm not saying ignore it. But this is the focus. So why am I saying this? Let's see. So basically, the reason is the course enables you to learn, and the lectures are designed especially for learning. But we will also prepare you for the exam. So as I said, my suggestion is focus on understanding, learning, and mastering the material. Lectures, readings, labs, homeworks, all enable this and prepare you. And reinforce your problem-solving skills with homeworks. Homeworks actually prepare you for the exam. And then do not worry about the exam while listening to the lectures. Do not worry about, oh, this guy is telling me about something. This guy meaning me. Is this going to be on the exam? Don't worry about that. You will see, I mean, not everything that I talk about can be on the exam, right? It's impossible. It makes no sense. And if we just focus on things that are going to be on the exam, that destroys the whole learning and scholarship that is the fundamental core of a university and progress, basically. So you cannot worry about that, I would say. I'm not going to teach you only what will be on the exam. I'm going to give you a much broader picture of ideas so that you can grow. But we will prepare you for the exam, as I will mention in a little bit. And again, most of you will pass this course. This is actually a course that has a passing rate okay, I'm not going to give you any side channels, but it's not the worst course in the world in terms of the passing rate. As you can see that number, right? Historically, 80%. And I think to fail this course, you need to work a bit harder. Okay. Okay, so basically we will release a lot of material to help you with the exam. So labs, for example, labs are, I think, you get 30% of your grade with the labs. Those are, in my opinion, if you do well in the labs, you get 30%. And then there are extra credit assignments, you get maybe 3 or 4%. And then the rest you need to make up with the exam so that you can at least pass if that's your only goal in life. Okay, so we will release a lot of material to help you with the exam. We'll have problem-solving sessions, exam guidance. And if you're extremely curious of what might actually come up in the exam, you have a long list of exams that we've already provided online. And again, predictor, you can train your predictor, neural networks, and figure out what might come up in spring 2023, right? Or what style may come up. You can see that there's a large data set over here. You can put it into ChatGPT and ask what questions may come up in spring 2023 exam, right? I cannot guarantee. You can actually try ChatGPT and figure out if it could solve these exam problems. I'm very curious. If someone does that experiment, please let me know. Some of them it can solve, I think, but I will argue that some of them it cannot solve. Okay, but basically we'll have a lot of problem-solving sessions that will come up at the end. Last year, you can see, I cannot read over here. You can see that there are 3 hours here, 3 hours here, 5 hours here, 4 hours here. These are all problem-solving sessions where TAs solve problems and show how you can think about the questions. And you can ask questions also. And these are actually questions that are from past exams, as well as homeworks. In fact, the homeworks that you will see have a lot of questions from past exams also. So homeworks are actually sample exams that you would be solving over the course of the course, let's say. Does that make sense? Okay. So the takeaway, learning is for life, it never ends. Exam study is until you pass. Hopefully August 2023. But you will probably have more shots if you don't pass August 2023. So that's why I say focus on learning and scholarship. Don't miss the forest for the trees, basically. The tree is here, that's the exam. But if you just focus on it, you will miss the forest, right? That looks like a tree. Okay, so that's why I suggest this sort of approach to this course. Approach as a learning experience. Think about long-term trade-offs and develop your critical thinking and decision-making skills, basically. If you don't care about the subject, at least use the subject for your benefit. And I think that's a good mindset of a lifelong learner, in my opinion. Somebody is giving you a lecture for 2 hours. Okay, I don't care about the subject, it's so boring. I only care about other stuff, which is fine. Everybody has different kinds of things they care about. But take advantage of those things so that you can actually improve yourself in those other things that you care about. I think this is not a bad proposition, in my opinion. Again, based on this, I think your mindset will determine what you get out of the course. This doesn't mention any grade, by the way. What you get out of the course is not the grade. What you get out of the course is, I believe, the improvement and the growth and the ideas and hopefully how this course will shape you into the future. Okay, so I would suggest, based on this, find and choose a learning style that works best for you. If your goal is just to pass the exam, I don't care, that's your goal, right? You're an adult, you're an individual, you can make decisions for yourself. I cannot force any decisions on you. I cannot say, why are you caring about the exam? Care about the exam, fine. And do whatever it takes to actually pass the exam then. And I believe we provide materials to actually enable you to do that relatively, I'll say easily, but you may argue, you may say that, okay, it may not be easy, but you can do it basically. But if you care about really learning and also passing the course in some way, I think that's a much better approach so that you can actually grow much better. Okay, so hopefully that makes sense. Any questions? No hands? Or nobody shouting yet? Okay, yes. Oh, okay. No, it's not a normal lecture. This happens after lectures end. So that just to prepare you for the exam, basically. So you're going to normally prepare for the exam probably after lectures end, but we help you with these problem-solving sessions. In fact, you can already use these solving sessions to, you can already watch these, they're all online, and some of the homework questions will be very similar to, or maybe exactly the same as what we've solved in the past. So if you really want to understand the solution of a problem, you can go to one of those videos, watch it, and then attend office hours, ask questions. Hopefully that makes sense. Basically, you can use the old materials for your purpose, but it's not going to happen during the course, let's say. Okay, that's a good question. Like, when does it happen? Okay, so let's continue that. So what will we learn in this course? Now I want to spend some time on learning and what's happening in the field. As I said, the goal is to learn how computers work from the ground up and why we care. So I guess the natural question is, why do we even have computers, right? Is it really useful? Maybe we should go back to not having computers. That sounds not so progressive, but anybody, why do you think we do computing? So that we can shout at each other on social media? That's what it's come down to, I guess, today, but that's not the only thing. That's my question. So I would say it's to solve problems. Maybe shouting will eventually get us to solving problems. We will see, but maybe it's not the best way. But the reason we design computers is to solve problems in the end. And why do we solve problems? So that we can gain insight, right? In the end, the goal is to gain insight so that we can do better in the future. And this is said by Richard Hamming. How many people know about Richard Hamming? Hamming distance, Hamming codes. Okay, so you may have seen it already. So he actually said computers are designed to gain insight, not crunch numbers. I'm going to talk about that later on. So why do we do that? Hopefully to enable a better life and future, right? These are grander goals in the end. Okay, I mean, we can philosophize about this, but let's talk about how does a computer solve problems. And in today's technologies, computers orchestrate electrons. Now we're back to physics, right? In physics, you may have learned about things like electrons and holes, and computers all orchestrate those things. In today's dominant technologies, at least. So how do they orchestrate electrons? Or how do problems get solved by electrons? Basically, we build a hierarchy. Electrons are things that can potentially solve problems. People have realized that. I'm going to actually mention Richard Feynman, who's a very famous physicist, later on today. But we cannot communicate with the electrons. We have some problems. We have a lot of problems. I don't know, climate, artificial intelligence, congestion. I'm going to talk about that also at a high level. I want to solve this problem. Electrons, can you please solve this problem? I've never seen anyone succeed with this sort of communication yet. Because we don't speak electron language, our interface doesn't allow that. And electrons don't speak our language, their interface doesn't allow that. We have a huge interface mismatch between us and the electrons, right? We have a better interface between us and the dogs, for example. We can communicate better. But dogs are not as good as electrons, it turns out, in terms of orchestration. Okay, so that's why we build this hierarchy. We translate the problem into some algorithms. And then algorithms are programmed in some language, and then they execute on system software. And they get essentially compiled down to some instructions that the lower level thing can understand. And that lower level thing is called microarchitecture, which we will see. And then microarchitecture gets implemented using digital logic, which we will also see. And digital logic gets implemented using devices that make up transistors. And transistors operate based on the principles of essentially electrons, right? So that's how we bridge the gap between problems and electrons. And this is called the transformation hierarchy. This is a narrow view of computer architecture. Basically, if you take a traditional computer architecture course, it will talk about the software-hardware interface, microarchitecture. This is not a traditional architecture course, and as I will show you later today, today's architecture is much broader, basically. Today, people design systems that take algorithms and adapt it to the devices, and design devices that actually can execute those algorithms much better. Today, it's much broader, basically. So we're going to see a cut across the stack over here. Of course, our core focus will still be on this part, but we will study logic so that we can get there. So your physics knowledge, we will not go below the abstraction of logic, if you will. The lowest level thing we will talk about will be the transistor. So, okay, we'll take this expanded view in this course, but that doesn't mean that we're going to cover everything in that expanded view. So let's go into this levels of transformation relatively quickly, because you've seen some of these things in other courses. And this is Richard Hamming's quote. The purpose of computing is to gain insight, not numbers, not to crunch numbers, basically. You crunch numbers so that you can gain insight, right? Like machine learning models today do that, right? There's a lot of number crunching going on. Hopefully it gives you some insight, hopefully useful insight, right? And that's Hamming with his cat. I like this picture. Okay, we gain and generate insight by solving problems. And that's why we have the hierarchy. So how many people have taken an algorithms course? Hopefully previous semester, right? That's good. How many people have not taken an algorithms course? No one. Okay, that's good. So basically, you probably know what an algorithm is. The algorithm is a step-by-step procedure that's guaranteed to terminate. It has a finiteness property, and where each step is precisely defined, stated, and can be executed by a computer. Essentially, it's finite, definite, and effectively computable. These are three major properties of an algorithm. And again, we're not going to cover algorithms in this course, but that's how we should express our problems as, so that they can be executed by a computer. And there could be many algorithms for the same problem. And as you already know, there could be many programming languages in which you can implement your algorithm. And then there are many system software. This stands for virtual machine operating system, memory manager, on top of which you can execute your programs. They aid the execution of the programs on a system. And then in at least general purpose systems, those programs are expressed in terms of instructions that we will cover. This is called the instruction set architecture. And we will see actually other properties of instruction set architecture in lecture 9 or so. This is essentially the interface, the contract between the hardware and the software. And this is what the programmer assumes the hardware will satisfy. And we will get to that. So this is what we will cover. We will also cover microarchitecture, which is essentially the implementation of the ISA. So ISA could be x86, for example, or ARM, or RISC-V today. There could be many, many implementations of this instruction set architecture, as we will see. Like x86 has implementations from Intel, AMD, and Intel has tens of implementations in the past. And today, AMD has tens of implementations, and there are other companies that also have implemented x86. And then microarchitecture gets implemented by digital logic circuits. These are the building blocks of microarchitecture. For example, gates are examples, and we will see that very soon, maybe tomorrow. And then logic gates are implemented using physical devices that operate based on the principles of electrons. So in this course, we're actually going to cover this red area a lot, but we're going to talk about the implications on the higher levels as well. So computer architecture, this is a general definition, is really the science and art of designing computing platforms. Computing platforms, basically, what are those? This includes the hardware, interface, the system software, and the programming model. So it's very broad, as you can see. It's science, because there are a lot of scientific aspects of it, but it's also art, because there are some parts that you cannot really completely scientifically model, right? For example, you're designing a computer architecture for 5 years down the road. You don't even know what the applications are, right? Maybe 5 years down the road. So how do you model this? So there's a lot of art that goes into decision making, and that becomes the art and science of trade-offs in the end. We'll see more about this. And the goal is to achieve a set of design goals. For example, your design goal may be highest performance. I want to get the highest performance on this workload XYZ. Pick your favorite XYZ, climate modeling, machine learning. Machine learning is a very general workload, of course. ChatGPT. Okay, let's make it more, let's say, specific. Don't think that I like ChatGPT, by the way. I just use it as an example because everybody knows about it, right? How many people know about ChatGPT? I should ask that. How many people do not know about ChatGPT? Don't be afraid. Sometimes it's good to be living in a cave and not learning about what might be going on. Sometimes you come up with the best ideas without thinking about what's going on in the world, actually. I like that. But yeah, basically, that's a supercomputer, for example. Or it could be something like this. You want the longest battery life at a form factor that fits in your pocket with reasonable costs, okay? Or a capped cost, as you can see. Or you want the best average performance across all known workloads that you care about at the best performance cost ratio. This is more general purpose computing, right? The middle one is kind of mobile computing, a specific type of mobile computing. So there are many, many, many types of computers, as you can see, and they're distinguished with their design goals. In the end, designing a supercomputer is very different from designing a smartphone, but many fundamental principles are similar. The building blocks that you will see that you get exposed to in this course are actually going to be similar in supercomputers versus my cell phone versus this computer. But how you use them will be different. How you make the trade-offs will be different. So we will hopefully see that. Just to give you a pictorial idea, as I said, this is going to be high level. We'll see different platforms like this. These are different platforms where what we're going to talk about is used. This is another platform. It has a computer. Another platform. Well, a joke of a platform, 1990s Mr. Bean. How many people know about Mr. Bean? Okay, that's good. Do you know how he's driving this car? Yeah, exactly. He's pulling strings. But this is a self-driving car, right? So he imagined these earlier. It's funny that he can trust this car. We will talk about security, safety, reliability. The question is, can we actually trust our self-driving cars without having that lever that we can use? I wouldn't. This is a self-driving car from old times. You can see that there's a big computer over here. This is a data center. It's designed for some purpose. It can execute many, many workloads. It's usually general purpose, but you can customize a data center also. This is a supercomputer that looks kind of similar, but it's completely different in terms of the purpose of it, right? So as a result, what goes into these systems internally is different from what goes into this system. These systems have a lot of accelerators, for example. Although data centers are actually getting closer, they're becoming more and more similar over time. But the workload customization is different. This is the Fugaku supercomputer in Japan. So I like these pictures, as you can see. I'm contrast these with the pictures that I'm going to show you later on architectures. These are actually similar to building architectures, right? There's some beauty associated with it. They solve problems, but they also have some natural beauty, if you will. This is a systolic array that we will see in lecture, I don't know, 24 or 25? No, 19, hopefully. But basically, this is used for matrix multiplication, matrix multiplication, and this is designed by Google. It's called a tensor processing unit. How many people have heard about TPUs, tensor processing units? Okay, fewer people. You will learn more about those. But these are at the core of what machine learning accelerators do today. Everybody needs these today. In fact, you have it in your cell phones, even though you may not know it. This one has something like that. We don't know exactly if it's like that, but it's a machine learning accelerator. So we're going to cover systolic arrays, fundamental principles that go into building these accelerators. This is the later, I believe, one of the latest generations of TPU, as you can see. Don't worry about the writing. Again, don't worry about understanding everything. I'm just giving you a high-level picture of what's going on in the field right now. This is Tesla's self-driving computer, circa 2019 or so, I believe. So this is another machine learning accelerator, actually. It does machine learning inference, for example, tasks like pedestrian detection, neural network inference, and they designed this for their cars. You can see that these are systems that are designed for specific purposes. They're not really general purpose completely, but they can be used within the context of cars. So you can argue that, why is Tesla designing these computers, right? Why don't they just use some Intel computer? Why? Because the workload that they have is extremely demanding. And they know what's going on in the workload, so they actually customize the chip, the hardware design, to the workloads that the car is supposed to execute. So that's what I mean by whole system design. You can think of Tesla as a car company, but maybe it's a technology company. I think a lot of these people who are dealing with large amounts of data or decision-making based on data need to design the entire systems from the hardware all the way to the software. There's another Tesla. I pick on Tesla because they actually are quite public about what they do in their systems. So what I showed you over here has inference. Basically, it makes decisions based on a trained model. But how do you train that model? They figured out that all of the data that they collect all over the world is a lot of data. How do you train your machine learning model so that you can install them on, I don't know, cars so that you can make decisions? They need some other computers for that. And this is their training chip, essentially. Again, numbers, you can see, actually, these are huge numbers. And this is a bit older, 2021, I believe. And you can see that they show the compute requirements of neural network training, and this is a picture of their system. I like this picture because it's kind of similar to what I have. It's a kind of a dumbified version of my transformation hierarchy. But this is what they say, basically. They build all of this. They build the chip so that it's efficient. They build the system so that it can take advantage of the efficiency. They build the compute cluster so that it can scale up to a lot of data. And they build the software, compilers, operating system, everything that is programming model, everything that's needed to take advantage of it, basically. So this is a machine learning training system at full scale. And it's essentially what I was talking about earlier. It's hardware, software, entire system design. And the goal in this course is actually to really understand how you can get there. Of course, we're not going to be able to cover software or compute cluster, but we're going to cover how we can start with the basics of making these trade-offs. This is another system. This is a GPU from NVIDIA in this particular case. Maybe it's the most powerful although it's very hard to keep up with these things, so don't take my word for it. But you can see that they're actually adding specialized instructions for dynamic programming. They claim very high improvements. How many people know about dynamic programming? Okay, that's good, the algorithms course. Yeah, dynamic programming turns out to be very important for genomics, genome analysis, for example. I mean, this is their claim, but you can see that people are trying to, even in a, so GPUs are actually a relatively special purpose system. They were designed for graphics because graphics had extreme compute requirements at the time in 1990s. Over time, people said, oh, this chip exists in my computer. Some really smart people said, this GPU graphics chip exists in my computer. It's doing graphics. Can I use it to do something else? And those people actually enabled the GPUs to do other stuff, like parallel computing. These are the most powerful parallel computers that we have today. And now they're more general purpose, but now they're also adding specialized instructions to do special things like dynamic programming, right? Because that's so important. So you can see now some trade-offs and tension between general purpose versus special purpose. Now, if you actually want to take advantage of high efficiency, high performance, you really need to specialize your system in different ways. Okay, this is another system. Has anyone heard about this? Cerebras? This is a chip that's this big. And it's just a chip. System is actually much larger. This is really a chip because it's a wafer, basically. Normally what you do is you have a silicon wafer, you cut it into pieces, and you have smaller chips like this, the largest GPU over here. Largest GPU looks very small compared to this chip. But these guys said, our goal is to accelerate machine learning, training and inference. And machine learning is very compute intensive as well as memory intensive. So why don't we put a lot of computation and a lot of memory on the same chip? Well, if the chip is small, you cannot do that. Why don't we have a much bigger chip? Trillions of transistors. And that's the idea over here. Of course, this leads to a lot of different design decisions in your system. How do you power this up? We're having difficulties powering up GPUs today. How do you power this up? What's the cost of this? What is the reliability of this? So there are a lot of actually interesting design decisions, but people are building these systems. These exist. And there are people who are buying these systems for good or bad. I don't know who they are, but I can assume that some people are buying it for bad purposes also. You can guess what they are, but they exist. Okay, so these are some genomics systems which we're going to talk about. This is a processing and memory system, actually. So these exist. We're going to talk about the reasons for this after we take a break soon. But the reason I'm showing you, well, one of the reasons I'm showing you these pictures is that all of these systems try to achieve high energy efficiency and performance on a set of applications, on a set of workloads, machine learning, for example, or genomics. And they take an expanded view of architecture. Basically, they don't just focus on microarchitecture. They optimize across the stack, basically. Some of these may build devices. Devices are actually harder. But there are some people who are actually designing devices as well. So they go across the stack. This is co-design or cross-layer design. You co-design across the hierarchy so that you can achieve better design goals by specializing the system as much as possible. And we'll see more examples of this in this course. That's one of the reasons why we have to focus on the cutting edge. So this is the state of the art today. If I actually give you a course that says, okay, here's a pipeline and we're done, I would be doing a disservice to you as future generations because a pipeline is 1960s, actually, let's say. You need to really know about the different components that may go into this chip, at least the design trade-offs and principles and basic ideas. Okay, before we take a break, I guess let me finish this one. So computer architecture, as I said, is a science and art. This is a more, let's say, deeper definition of computer architecture. It's science and art of designing, selecting, and interconnecting hardware components and designing the hardware and software interface to create a computing system that meets a bunch of goals. It is functional goals, performance goals, reliability goals, energy consumption goals, cost goals, and maybe other specific goals. There are actually many, many metrics that go into the design. Some of these are extremely important, some of these are less important. And you can make trade-offs. Security goals also. If you're designing a fundamentally secure system, maybe you should be designing a very different system than these, because none of these systems are fundamentally secure. And we will see that, at least a glimpse into that later on. So basically, why do we want to study computer architecture? Hopefully, we'll enable better systems. We can make computers faster, cheaper, smaller, more reliable. We can enable new applications. Nobody imagined machine learning revolution, but machine learning revolution actually happened because of GPUs. Some smart students said, I can actually do the machine learning training and inference on a GPU, basically. And they actually did that. They customized things, and they actually showed that they could do it in the early 2010s. That's why the machine learning revolution you're experiencing today has happened. It needs another revolution to make things a lot more efficient, of course, but let's not get there. Maybe personalized genomics, personalized medicine, these things can be enabled also in the future. We can enable better solutions to problems because software innovation is really built on trends and changes in computer architecture. That's the reason, again, GPUs are a great example of that. And hopefully you can understand why computers work the way they do so that you can fix the problems and you can actually be a better designer. So today is actually a very exciting time to study computer architecture, actually, because there are many, many potential system designs possible, as I showed you. I'll show you more examples. And there are many difficult problems. So we'll cover some of these problems and goals in the second part of today after we take a break. But these give you some ideas, right? We have a huge memory bottleneck today, actually. We're facing security and privacy issues. These are things that actually these other earlier systems did not even discuss that much. So, and there are no clear definitive answers to these problems. And it's exciting because the computing landscape is actually very different today compared to 10 to 20 years ago. Applications and technology demand new architecture. So as a result, I mean, this is an old picture, but every component that we design today, like even inside here or here, as well as their entire system designs and their interface are being re-examined. So you can actually change a lot of things today, but you need to really understand what's going on first. So this is an example system in your pocket, actually. What I showed you earlier exists in your pocket. Well, if you have an iPhone, it exists like this in your pocket. And this is an M1 Ultra, I guess. You may have a much more expensive iPhone than me, which actually has even more power, let's say. So these already exist in your pocket. And this is an example of a system that also cuts across the stack, basically. There are a lot of accelerators inside there, which we will also talk about. Okay, so this is a good place to actually take a break. Wow. Okay, I like 10-minute breaks. So let's do a 10-minute break. Get back at 15:20. And then we will continue more high-level stuff today. Tomorrow, we will go into more detail on topics. This okay is better, I think. Can you guys hear me, everyone? Let's get seated. Okay, let's continue our lecture. So far we've covered a bunch of systems at a very high level. Hopefully this gives you an idea of what you may find. For example, in this picture over here, we're going to see a lot of things that go into the execution of programs here, caches, memory hierarchy. We're going to study all of that basically. So I find this very exciting. But if you really want to have a full picture, you should study everything over there, which requires multiple courses. Let me give you quickly some idea about this transformation hierarchy. So transformation hierarchy is interesting because you can enhance systems with innovations everywhere, right? Innovations can be driven by technology. Innovation can be driven by algorithms and architectures. Basically, all of these parts you can enhance. And there's very, very interesting things that people have been talking about. You may have heard of this beautiful lecture by Richard Feynman, who's a very famous physicist of the last century, I should say. Basically, he gave this lecture at Caltech in 1959, where he said that there's plenty of room at the bottom. He's referring to the bottom of the transformation hierarchy, physics, basically. There's plenty of room in which we can improve our devices. These fundamental devices and fundamental ways of building transistors, for example. And that can enable us to, for example, directly manipulate individual atoms at a more powerful form of, as a more powerful of a synthetic chemistry than used at the time. So this is actually very interesting, I think. So there's a lot of innovation that's at the bottom that has enabled a lot of things today. Like we're going to talk about scaling, Moore's law, technology scaling. And that has enabled us to put a lot of transistors on a single chip by reducing the size of the transistors. But it's not just reducing the size of the transistor. That's not enough, basically, because you need to actually do other things to make sure that the transistor operates well. And all of these are at the lower level, at the bottom layer that we're not going to talk about. These are microelectronics and physics. And essentially, you can see that he was particularly interested in possibilities of denser computer circuitry. For example, microscopes that could see things much smaller than is possible with scaling electron microscopes of the time. And he also presented the possibility of swallowing the doctor, an idea that he credited in the essay, blah, blah. Essentially, the concept involved building a tiny, swallowable surgical robot. A lot of things you can imagine because you think about the possibilities of the underlying technology. So as an architect, you should always think about what is the underlying technology and how can I make it better and how can I actually take advantage of it better. So this is really important. So looking at emerging technologies, and I will mention some of these during the course of this lecture. But don't forget the other parts of the stack also. Today, some people think, and I don't necessarily agree, that the innovations at the bottom are more difficult, have stopped. Of course, everything is more difficult, right? Because we've progressed a lot. But maybe we're not thinking creatively enough. So I think there are people who are actually trying to do a lot of innovation at the bottom layer of the stack. So let's not dismiss that. But it's true that it's difficult. It's become difficult. It didn't stop, basically. I believe there will be more innovations, breakthrough innovations, actually, within the next 10 years. But we should also look at other parts of the stack. And these folks kind of state the obvious, if you will. They basically say that if technology scaling stops and you cannot improve the devices, other stuff will be more important. Well, it's kind of obvious, right? But it makes sense to state it sometimes. Stating the obvious is actually useful for people to really understand what's going on. And these folks basically say that growth in computing performance will still be available, especially at the top of the computing technology stack, transformation hierarchy, software, algorithms, and hardware architecture, and co-designing the systems. And that's what's happening today. But I think we need to actually make sure we have developments across the stack. So there's plenty of room, in my opinion, both at the top as well as at the bottom. But you can actually exploit it much more so when you communicate well and optimize across the top and the bottom. And I think this is what a lot of innovative people are trying to do today. That's why we have this expanded view, basically. Okay, any questions so far? Now I'm going to give you some more, basically. What's happening in computer architecture today in a different perspective, let's say. So we basically have a lot of issues. We still need more higher performance, energy efficiency, and sustainability. These are, if you were taking a course in computer architecture in the 1990s, and if you're taking a course that's structured just like a 1990s course today, which is not this course, you would be talking about only performance. But energy efficiency is actually a very, very big constraint today. I'm going to give you some examples of this. And sustainability is very intimately tied to energy efficiency. Although sustainability is a broader concept because it's not only about energy, it's also about the lifetime and also degradability or biodegradability of the components that you design as well, right? So those are some issues that are driving the computer architectures today. But there's also more: reliability, safety, security, privacy. I'm going to give you some examples very quickly of these. We have much more demanding workloads than in the past. In no time in human history, we've had this data deluge, if you will. It's crazy, basically. You can generate data everywhere today. Right now, we're generating a lot of data. It's getting stored in Zoom somewhere, for example. It's getting live streamed. But a lot more. When every click you do on the internet gets recorded somewhere by someone, and that's data. There are video cameras everywhere that are generating a lot of data or recording a lot of data. And there's the machine learning that we talked about briefly. And then there's new device technologies that are also happening today. I will not focus as much on these, but these are four major things I would say that are really, really interesting today in computer architecture. Okay, so let's take a look at examples. Actually, some of these I think we've already seen, but I'd like to give you a bigger picture also. Basically, as we design computers, they actually consume a lot more power. We've already talked about ChatGPT, for example. I think we should also think about the responsibility for the future. Do we want a future that looks like this? Looks nice, right? Or this? Who would take this one over the previous one? Okay, fine. You're entitled to your choices. I'm not judging anyone here. Who would take this one over the next one? Okay, that's a bit better. I would argue that, I mean, this is of course metaphorical, right? It's not, but basically I would argue that we need all of these at the same time: high performance, energy efficiency, and sustainability. And ideally, we would like to do it through this sort of future that's livable and breathable, let's say. So there are many difficult problems we need to tackle. So computers actually affect this future. We will discuss that. But there are many difficult problems that we need to tackle to build a better future. And computers actually enable us to tackle those problems as well. So computers are a double-edged sword in a sense. They are there to solve our problems, but to be able to solve problems, they actually cause trouble, like consuming a lot of power and becoming not so sustainable as well. If you study the data centers, for example, data centers that we build today are actually very, very bad for the environment. They are put in places where there's plenty of water sources so that you can cool them. So they actually affect the environment where they're in. Plus, on top of that, they actually consume a whole lot of power. So we're building these computers to solve problems, sometimes to do useless things also. Some of you may be guilty of that also, just like me. But basically, essentially, computers are also generating a lot of overhead for us as well. But let's take the brighter side. We have a lot of problems to solve. We have a lot of problems to understand. Intelligence, for example. How do we get to general intelligence that's good enough? I think we're very far from it, because this machine is much better than what we can do today in many, many aspects. And there are many, many papers that are written about how much energy and carbon emissions happen because of the machine learning models of today. These are actually older models. This is from 2019, I think, as you can see. Training a single AI model, a single machine learning model can emit as much carbon as 5 cars in their lifetimes. Now, people are making projections about ChatGPT. I didn't put any of those over here because I think they're a bit more speculative. It's a nice article. It's much bigger, basically. And any inference that you do with ChatGPT, if you start talking to it, it's wasting a lot of power, basically. So think about the environmental implications of what you're doing with this thing. Okay, but intelligence is a problem that we want to solve. The question is, can we get there and solve it in a much more sustainable way? There's congestion, things like this. There's public health, which we are going through. There's genome analysis, which actually a lot of data is generated. Today, you can actually sequence a lot of genomes because device technologies have enabled us to sequence a lot of genomes at high throughput, low latency, low cost. And you can see that curve over there. That curve shows that basically this is the cost per raw megabase of DNA sequence. It's going down, and then it went down a lot more with the high throughput sequencing technology, and it's going down even more with nanopore type of sequencing technologies. And this is the curve, the cost of a transistor, if you will, Moore's law. So basically, genome sequencing technologies are scaling much better than transistors today. As a result, they can generate a lot of data. A lot of countries have genome centers, if you will. The question is, of course, it's useful, hopefully, to analyze this data, but can we do it efficiently, is the question. And this is another example. This is from Cerebrus's chief architect. It basically shows the exponential growth of neural networks. You can see the model memory requirements on the x-axis and total training computation requirement, petaflop days, on the y-axis. And they're both growing. They're increasing, actually. Both of them are increasing exponentially, if you will. So you can see the numbers over here, basically. 1,800x more compute in just 2 years. That's why this is becoming unsustainable, in my opinion. And then we also have the computation and storage. We want both computation and storage, as you can see, in these systems. But we have a dichotomy between them also. Computation happens here, and then data storage happens in the memory devices. We will talk more about these. And it turns out a memory access going to main memory is much more costly in terms of energy compared to computation that you do, a sophisticated computation that you do. So the energy cost of a main memory access to get the data from main memory, I'm not even talking about storage. Forget about storage. Storage is much worse. But main memory is 100 times or 1,000 times more costly than a computation. And if you actually do simple computations, this number becomes much higher. So think about it. Computation is very cheap, but accessing the data over some interconnect, even from main memory, like inside this computer we're talking about, there's a 6400x difference. Imagine accessing that data over the internet. Now you're exercising a lot more interconnects and a lot more components. That's even higher, actually. So it's good to do these studies to understand. So basically, we have a huge dichotomy between computation and data access. As a result, people are looking into computing architectures with minimal data movement. How can we minimize the data movement? How can we reduce the amount of or the length of data movement, if you will? That's why people are actually combining computation and storage in the same chip in some cases. And this is an example. This is a startup in France that combines DRAM, main memory essentially, and that puts processors inside main memory so that you don't need to go off chip to actually get the data. So these are some concepts that I want to give you, but you're not going to be responsible for this clearly. So these are some real memory modules, basically, you can see. And these are useful for many applications. You can accelerate applications using FPGAs, which we will talk about in your labs. You will study FPGAs, but keep in mind that FPGAs are not just devices that you can model hardware with, which you will use them for, but you can accelerate applications with them also because they have reconfigurable logic, and you can reconfigure the logic to match the application's requirements. And this is real in industry also. For example, Samsung, which is perhaps the largest semiconductor company in the world, is developing chips that can combine, again, memory and computation so that they can accelerate machine learning, as you can see. I'll skip some of these things, but you will see actually some of these pipelines. These are actually really simple pipelines, much simpler than what we will study in lecture 19 in this course. Okay, we will study instructions also. So these are actually, all of these things that we see today are based on the fundamental principles that we will study in this course. You will see some of these instructions also. I'm just showing you that something interesting is happening today. So recommendation, deep learning recommendation, good or bad, people use it for stuff. To predict what movies you're going to watch next, for example. YouTube does that a lot. Or you may want to watch next based on what you watched in the past, and many other side channels that you've given to YouTube over your lifetime. Basically, a recommendation system can be accelerated by putting a lot of memory and a lot of computation together on a module like this. Why? Because it's bottlenecked by both computation and memory, and people don't want to move the data between the memory and the computation units. Okay. Okay, you can see that another major manufacturer is also putting memory and computation together. And you can see system manufacturers are also doing similar things. These are actually real systems that people are building today. Okay, also people are writing papers. This is a topic that we work on in my research group, but you can see that there's a lot of research that goes into these systems as well. I'm not going to talk about this, but if you're really interested, you can watch lectures. Another example is a device technology. This was introduced in 2019. This is a main memory that you can buy, that you can install on your computer. It's non-volatile. Basically, when you power off your system, the data doesn't go away. This was not there for many decades. Your storage, disk is different. Disk is non-volatile. Everybody knows that, but main memory, when you power it off, everything gets cleared because you lose the data and you lose the data. But here, once you have non-volatile main memory, you can actually get access to data much faster because you don't need to load it from the disk. And this has properties that are much more similar to main memory. So this sort of thing also can reduce the data movement overhead in systems. Now, unfortunately, this is an example of emerging new devices. And Intel decided to discontinue it, I believe, because they have made a lot of bad decisions over the last 5 years or so. So they're struggling. I believe there will be more devices like that will come. But there's a lot of investment that goes into things like this to make this happen. A new device technology requires essentially research and development across the entire stack. You cannot just come up with a device. You need to actually enable an entire system in the end. Okay, we've actually done a lot of research on this topic, but I'm not. That's why I like this topic a lot also. But I'm not going to talk about this in more detail. Okay, we've already talked about this wafer scale engine. As you can see, this is an older version, this is a newer version. And again, the goal over here was to put a lot of compute and memory together, close to each other on a chip. And the way they decided to do that was to have a huge wafer scale chip, right? Otherwise, how are you going to put a lot of memory and computation together? Well, one way is what other companies are doing. Put computation inside the memory chips. But these guys, unfortunately, they don't have access to the cutting edge DRAM technology. So they actually put computation, to put a lot of memory inside a computation chip, if you will. So we will see that dichotomy more. But I think people are trying to bridge the gap between memory and computation a lot today because of the data movement bottleneck. Okay, so this was just to give you an idea of what is happening. Basically, people are designing computer architectures to minimize data movement. And hopefully that will enable us to have much more fundamentally energy efficient architectures because data gets processed where it resides or where it's produced, doing computation inside the sensors, for example, inside the cameras, where the data is captured. Those are actually very good paradigms. And there are some other emerging device technologies like 3D stacking that can enable this. Instead of putting chips in a two-dimensional manner, you put the chips in a three-dimensional manner and connect them much more tightly using things like carbon nanotubes, for example, different essentially emerging technologies. They actually enable much computation immersed inside the memory as well. That improves energy efficiency as well as performance. So it turns out these improve both performance and energy efficiency, and I believe sustainability as well. So these are called data-centric architectures today. A lot of what we will cover in this course will be compute-centric architectures. We're going to assume memory is somewhere else, and then we bring the data into the processor and do computation, and we write back the data to the memory. But data-centric architecture doesn't do that. Data-centric architecture, memory and computation are much more coupled to each other. So keep these in mind, basically. Okay, so there's another trend that's happening today. Again, motivated by performance, higher performance, energy efficiency, and sustainability. Everybody's essentially designing accelerators. This thing over here has tens of accelerators in it. And this is that thing. I believe I have this version. It's a system on a chip. So a GPU is an accelerator. You have vision core somewhere over here. You have neural engine. This is a system on a chip, but there are other components also over here. So you can see basically, and people are building more powerful systems. This is M2. I don't know. I don't keep up with this all the time, but you may have the M2 basically if you bought it recently. People are building accelerators on YouTube, for example. This is YouTube's video accelerator. People are dealing with videos so much that they have to design an accelerator that's specialized for video encoding and decoding. Otherwise, it's too energy inefficient and it's too low performance for them. Google made the decision that if they design their own chip for video encoding and decoding acceleration, they save a whole lot more cost in terms of power, as well as buying these chips from other people. So these people are actually designing systems for video acceleration, as you can see. And this is actually beautiful if you're interested in looking at it. It's a very special purpose chip, as you can see. It's encoder and decoder cores, basically, and the CPU is at the bottom left over here. So you can see some major chips today are not general purpose, although they can be general purpose because they have a CPU over there also. Okay, so you can actually read articles about this also. We've already seen some of these things, so I'm not going to talk about this. Clearly, neural network inference and training is another example that's driving these accelerators, and many, many companies are building accelerators like these. And we already talked about these Google TPU generations. Again, we're going to see the fundamental principles of a lot of these in our lectures, systolic arrays, for example. But these are not just point examples. It may have been a point example in 2015, 16, 17, but today, essentially everybody who wants to be competitive needs to design their entire hardware and software stack together. This is a picture from one website. I think this is actually from 2019, so this is 2021, but I downloaded in 2021, I guess. Okay, so this is why the axiom that I said actually holds. Well, there's empirical evidence to show that this axiom holds, right? Basically, everybody is designing, taking an expanded view of computer architecture to design these platforms so that they can specialize as much as possible within the design goals. Any questions? Okay, this is still high level. I'm going to now switch to something a little bit different. Reliability, safety, security, and privacy are also very important problems, actually. And we're having trouble, basically, in today's systems. There are many, many aspects to reliability, security, safety. But I'll focus on unreliable hardware as an example. So this is an example of unreliable hardware. Does anybody know where this is? Yes? Yes, Tacoma Narrows, yes. I used to live close to it. I never crossed this bridge because this happened to it in 1940. And then they built two bridges. That's called dual modular redundancy. If one bridge fails, maybe the other one will not fail, right? Hopefully. But if you have a common mode error, both of them may fail at the same time. So in reliable system design, you should avoid common mode errors. You should randomize the components such that they fail in different ways, if you will. Right? Of course, if you want to be more reliable, you should build 4 bridges in parallel, and they randomize it such that they don't have any common mode errors between them. Right? Okay, but this is what happened to this bridge in 1940. You can watch videos of it. This is another view. This was not fatal. I actually have a collection of these bridges, which I can show you some other time, not today. But I think of this as a data reliability problem. And if you think bridges are important, and I believe they're important, human beings have been building bridges for thousands of years. We've made progress, not bad. But computing is a lot more important today. If you think about the scale of things, bridges are limited. Computers are, okay, yes, they're limited also, but comparatively, they're everywhere, a whole lot more. And they're making decisions much, much more important. Well, bridges are not making decisions for us, but the computers are making decisions for us. So basically, if you really care about this sort of problem, you should be caring about computer problems a whole lot more. I think people don't think about it from this perspective in general. So we miss the big picture with computers. So computer reliable problems are much worse. So this is another example. You may care about this a lot more because there are people on it. So these people are very happy. But if a bit flip, a data corruption happens on that rod, they may not be happy in the next second. So I think of security as preventing unforeseen consequences. I believe safety is also similar to this. Dependability in general, robustness in general is about preventing unforeseen consequences. The question is, how can you design systems that can be fundamentally secure, safe, and reliable and dependable? So it's good to ask this question, basically. Of course, imagine a cutting-edge self-driving car, not Mr. Bean's yo-yo self-driving car over here. Can you depend on this platform? How safe and secure is this? Yeah, good question. How many people know about RowHammer? This is one of my favorite topics. Yeah, some people. How many people do not know about RowHammer? Okay, you'll have to fix that. Okay. So we'll talk about RowHammer very briefly, but this is a fundamental security vulnerability in all memory chips that is manufactured essentially by all memory manufacturers, that goes into all of the computers today, that exists in your systems today. And we've worked a lot on this problem starting in 2012, and this was our original paper in 2014. But I'll give you an idea of what this is basically. People draw pictures like this. It's not my picture. I like it though. It's art. So basically, RowHammer refers to the fact that you can actually predictably induce bit flips in all DRAM chips today. All DRAM chips that we keep testing are vulnerable today. And it's really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability, because someone can induce these bit flips, basically corrupt the data, and take over your system based on that data corruption if they know what they're doing. If they're a malicious attacker, for example. So there's a tenuous connection between reliability and security, as we will discuss later on. If you get a bit flip, if you get an error, that error may be something you can say, oh, I have a reliability problem. But if someone malicious takes advantage of that error, now you have a security problem at hand. And security problems can be also safety problems. If someone induces bit flips in your self-driving car, well, good luck driving it, let's say. Okay, but basically, people are writing articles like this. Forget software, now hackers are exploiting physics, because it's really a physical phenomenon that leads to these bit flips. I'll give you a high-level idea. So this happens in all main memories today, basically DRAM. And if you think about it, actually, DRAM is a bigger cost of the system today than CPUs. If you think CPUs are really important, think again. Memory is a lot more important today. Memory and storage is a lot more important. If you go to a data center, the biggest cost is about memory. And the biggest reliability problems are in memory in general. Okay, but if you look at memory, it consists of rows of cells. Again, think of these as rows that are storing data. Each cell stores one data over here, one bit. And what you can do to memory is you access one row and then read some data. That's underlying technology, you apply high voltage to that row. We'll see this later on in this course. You apply high voltage. That opens the row. Now, if you actually want to access some other row, you close the row. You apply low voltage to it. Now, if you keep doing this repeatedly, activate precharge, in DRAM it's called activate precharge, open or close, open or close, open or close. It turns out the rows that are physically adjacent that you did not access at all get bit flips. So data gets corrupted over there. That's the RowHammer problem, basically. So obviously, should this happen? Well, it should not happen, right? This is not what should happen. You're just reading some data from memory and you're destroying some other data. That data may be belonging to some other application. It may be belonging to your program. It may be belonging to some really security critical application that stores some private keys, for example, in memory. So basically, you don't know what is happening. And this should definitely not happen. But it's happening in modern DRAM chips. So we call this the hammered row, and we call these the victim rows. And we basically show that at the time, more than 80% of the chips from 3 major DRAM manufacturers are vulnerable. And these are the 3 major DRAM manufacturers that essentially contain more than 99% of the market, I believe. So if you get a DRAM chip, it's likely vulnerable, but we show that actually other chips are also vulnerable. So 100% today, because the vulnerability became worse over time. And the reason this is happening is it's a physical phenomenon. When you're accessing some location, there's electrical interference that's happening. This is again a high-level explanation. There's, of course, a lower-level device-level explanation also. But there's electrical interference that you're causing between these cells. The application of the high voltage causes interference. As a result, data stored in close-by cells gets interfered with, and they leak their charge, and they lose their value if you do this hammering enough times, if you will. I think it's fascinating. But this should not happen. The reason it's happening is our memory chips are very dense. Why do we want dense memory chips? Because we have a lot of data to store. That Apple M2 has 24 gigabytes of LPDDR. 24 gigabytes. It was unimaginable. My first computer, I believe, has 4 kilobytes or something. Something like that. 24 gigabytes in a cell phone. We're talking about a cell phone. There are systems that have terabytes of memory. These are data center systems usually. So these bit flips can be happening. And basically, people have shown that you can take advantage of this to take over a system. I'm not going to talk about this, but when we get to lecture 25, virtual memory, I'm going to circle back and talk about how this sort of data corruption gets circumvent all of the existing security mechanisms, because there's nothing that prevents this today, except for hardware solutions that are being added right now, which are not fully secure actually. But we need to think about these issues basically going forward. Okay, I like this analogy. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. This is from a famous hacker that is characterizing RowHammer. That's the beauty of Twitter. Sometimes you actually hear from good people some good analogies. If you follow the right people, I guess. Okay, so I'm not going to talk about RowHammer more, but there's a lot of interesting stuff that's going on this, and we talk a lot about this. And if you really want a 20-minute introduction to it, you can watch this. But there's a lot of security research also that's happening. This is software security people. They basically saw the idea, saw these bit flips. They said, we can take advantage of this. We can actually gain unrestricted access to systems of website visitors. If you want to figure out how they do it with RowHammer, you can read their paper. If you want to figure out how they can take over your phone without you knowing about it, you can read about this paper. If you want to figure out how they can leak your private data, you can read that paper. And these folks actually show that neural networks become much worse if actually bit flips like this happen. For example, this paper shows that an otherwise reasonably accurate neural network, it may be doing pedestrian detection or whatever, pick something. It may be doing something important that's safety critical, basically. It can turn into a neural network that's essentially terrible in terms of its accuracy, and you may hit a pedestrian if someone actually does these bit flips on that neural network inference machine. It could be an accelerator, or it could be a CPU or a GPU, basically. So basically, this sort of lack of dependability in fundamental hardware leads to lack of trustworthiness in hardware. And this question actually becomes very important. Can we truly depend on computers? Clearly, this question is across the stack again, right? Can we depend on the software? But if you cannot depend on the hardware, can we actually depend on anything, right? If hardware is actually having these problems, you cannot actually depend on anything that's built on it. That's what all of these works have shown. Okay, how many people have seen these pictures? Spectre and Meltdown? Okay, these were more popular in 2018. When I asked that question, everybody raised their hands. These are less popular, but these are also other security vulnerabilities. These are side channel vulnerabilities where someone can access your private data because of the way a CPU operates. And we're going to see a lot of these principles that lead to those side channels, that data leakage, information leakage from the CPU, if you will. Yeah, basically we're going to cover this, but we're not going, maybe we can circle back and see how these work. I'm not going to talk about these. There are more recent works from Google and Facebook that basically say we have a new problem. I mean, if you know what's going on, it's not a new problem, but they're really seeing the effects of this problem today. There's silent data corruption in cores. Some cores basically do erroneous computation for whatever reason, because they may actually they may have a bit flip somewhere in the core, basically. As a result, they get wrong results. And these people are writing papers about it, showing that data. And this becomes much worse at scale, meaning if 1 out of 10,000 cores have this problem per day, but if you have millions of cores in your data center, you're going to have this problem many times a day, right? So at scale, these become much worse. So bit flips, data corruptions are actually things that people are very worried about. There are also other security, privacy issues that I'm not going to talk about, but this is actually a very, very vibrant area How can you defend against malicious hardware, for example? You specified the hardware and someone manufactured it, but you don't trust the manufacturer. How do you ensure that the hardware actually is secure? How do you ensure that they didn't have something malicious in there? This is actually a big problem that people are concerned about, and people are trying to design mechanisms to ensure that that doesn't happen, but it's a tough problem, basically. Okay, so more demanding workloads, that's also happening. I'll go through this relatively quickly because we covered a lot of these, as you can see. And applications are increasingly demanding, and never underestimate people's imagination to build new things. So there was a time in 1980s when people were building MIPS processors. We will talk about MIPS in this course a little bit. MIPS is an architecture. And they built the MIPS R2000 processor, which is kind of similar to what we were going to cover in the lectures. And some people said, we don't need anything else. This is fast at executing everything. That was a very terrible, regressive comment, if you will. So clearly we have come through and we needed a lot of things. It's not also like we needed a lot of things. The faster computers enabled other things that people imagined, like neural networks today. So never underestimate, if someone tells you we don't need anything else, that's a very backward comment. That's against progress, if you will. Okay, so again, there are some new genome sequencing technologies that enable a lot of things. This is actually something that you can buy for yourself, if you will. But again, getting data out of it and analyzing the data becomes a performance energy bottleneck. It's not able to do computation today, for example. Why do we care? This is actually a slide that I used at the beginning of COVID. This was one of the last lectures that I delivered before we went into online mode. And I showed this picture. These are nanopore sequencing devices were being shipped to China at the time. And then it became all over the world. But to sequence the RNA of the COVID virus. But you can also make it even more aggressive, and you can do profiling. There are studies, for example, in the New York City Metro. People have actually sampled different parts of the subway, and they're trying to figure out what's going on in the subway. What kind of bacteria are there? What kind of viruses are there? What's lurking here, basically? Can we predict what's going on? Can we predict the next pandemic? So this actually, you can imagine how data intensive this task is, right? If you're collecting data all over the world and trying to figure out what's going on, that may be a way of actually figuring out what may come up next, if you will. Okay, so outbreaks are not new, basically. There's a lot of outbreaks that have happened in the past. Hopefully we'll take our lessons. But genome sequencers are becoming better, and they're becoming smaller, as you can see. As I said, you can actually sequence genomes much more. The problem is computational, basically. We have these sequencing devices that are extremely good, but for analysis, for scientific discovery or medical advancements, we need to do a lot of computation and data movement. And basically, we're bottlenecked by computation and data movement, very similar to machine learning. But this is a much more complicated, and in my opinion, much more interesting problem, because some of these steps over here involve machine learning itself. So it's a broader problem than machine learning, if you will. So, okay. So there are many benefits of scalable and faster genome analysis, scientific, medical, public health, etc., which we're not going to talk about. But this is another area that we work on, actually. When I was at Microsoft Research in 2007 or so, we were imagining embedded devices that can perform comprehensive genome analysis and give you answers within a minute, very quickly, basically. Today, we're not there yet, but we have made a lot of progress. There are many, many questions you can ask, for example. I will not bore you, you can read these, but what potential virus and variants might be lurking around, for example. And we've done a lot of work. Just to give you an example of what's going on in the field, people are trying to accelerate software using software mechanisms. Eliminate useless work is actually a very good thing to do, because a lot of software has a lot of useless work. If you can identify the useless work and get rid of it, your software will be a lot more efficient. And we did that. You can use hardware to accelerate things. And over time, you can use FPGAs. And we did in-memory acceleration, because this is very, very data intensive problem. And hardware, algorithm, architecture, co-design. Again, system designs. These are some algorithms that can be accelerated in hardware much better. Again, I don't expect you to read these, but this is just an idea of what's going on in the field. And you can see that these are cutting edge works. This is wrong, this should be 2022. But basically, there are a lot of algorithmic problems where you can design new algorithms as well as new architectures together so that you can do genome sequence analysis much better. We've talked about FPGAs very quickly. So I'm going to, okay, I will mention COVID-19 sequencing a little bit. Actually, this can be relatively fast depending on the analyses that you want to do. If you want to do very sophisticated analyses, that 7 hours goes to 7 days sometimes, and computation becomes a bottleneck. And if you're interested in this, I'd recommend looking into it because this is quite interesting, I think. I think COVID-19 is a very special case. There's a lot more that we need to understand. So I think we're still at baby steps in terms of our genome analysis systems. If you want to know more about this, this is a paper that's relatively short to read. And we also write a lot of beginner readings on genome analysis. This is hopefully beginner. Okay, so recall our axiom. These genome analysis systems are also entire systems that span devices to algorithms. We don't say, okay, let's design a microarchitecture for this. We say, how do we design the algorithm and the microarchitecture together? Okay, I think this is a good place to stop. Tomorrow we will pick up from here, and then we will delve into a bit more detail on the, let's say, we'll go from motivation to actual topics that we're going to cover in this course. Okay, see you tomorrow.